This is your pre-lab video for complex ions and amphoterism. Our objective for this lab is to make observations of different complex ions and their behaviors, and then use those observations to identify which ions are in an unknown mixture of ions that you'll be receiving at the end of the lab. So what are complex ions? So these are metal cations that are surrounded by things called ligands, and ligands are often very small molecules, small polar molecules. Some examples of ligands that we'll be using in this lab are ammonia, water, and the hydroxide ion. And these small molecules or ions form coordinate covalent bonds around the metal cation. And we call this a complex. The complex can be an ion or it can be neutral. An amphoteric substance is one that can behave as both a Lewis acid and a Bronsted base. Some examples are found with metal hydroxides, and we're going to be using this in lab quite a bit. An example of an amphoteric hydroxide is aluminum hydroxide. And we typically would write this as AlOH3, but really more accurately is this aluminum ion is surrounded by 6 different entities, and 3 of them are hydroxides and 3 of them are waters. Our metal hydroxide can act as a base when it's reacted with an acid. So note that we have 6 waters in a complex ion versus the 3 waters and the 3 hydroxides. The metal hydroxide can also act as an acid since it reacts with the base as follows. So this is the same aluminum hydroxide that we started with, but now we're reacting it with hydroxide ion. And you can see that one of these waters, instead of H2O, there's 3 of them. In this now there's only 2, and we have 1 more hydroxide. And this is an ion, so our ion is soluble now in water. So this precipitate, this solid, is redissolved. So aluminum hydroxide is said to be amphoteric. Now only certain cations will show the amphoteric behavior. So since some will and some won't, we can use this in separating different cations. The commonly encountered cations that form the amphoteric hydroxides are shown here. And this is a typo. This should be plus and plus. So these are the ions that you can expect to redissolve in excess hydroxide. Part A of your procedure is to test the ions as separate entities. The solutions that you will be making these observations on are separate solutions containing the following ions. So the first step that you need to do is to make observations of what these things look like in solution. Write down any color that these have or anything else that you can observe. Then you'll make metal hydroxides with all of these ions. Now follow the procedures that are in the lab manual and make observations as you go along. Your observations are your data in this lab. Part of the procedure will ask you to use pH paper to ensure that a solution is basic, for example. Now, you don't want to place your pH paper directly into your test tube and into your solution. Okay, that contaminates it. Use your glass stirring rod. Okay, so stir up your solution, and then your glass stirring rod will be wet with your solution, and just remove that and touch it to the pH paper to test for acidity and basicity. Red pH paper will turn blue in basic solution. Blue pH paper will turn red in acidic solution. Once you've created your metal hydroxide and made your observations of what these hydroxides look like, you need to test each of these hydroxides for amphoteric behavior. So will they redissolve in excess NaOH? That's really what you're looking for. Then you'll move on and perform reactions with aqueous ammonia. Now, aqueous ammonia has a dual nature. It can act as a weak base. When it reacts with water, it gives OH ions in solution, just as what's provided here. So ammonia in water actually gives us ammonium ion and hydroxide ions. This is weak, so this is a reactant-favored reaction. So we don't have a lot of these in solution, but we do have some. So it can provide the hydroxide ion necessary to precipitate many of the metal hydroxides. So if you added ammonia, you could precipitate the aluminum hydroxide. But the ammonia molecule itself can also act as a ligand and can also form complex ions with the transition metal cations. So for example, if we have nickel ion, and usually we would just write this nickel plus 2, but actually the nickel is surrounded by 6 water molecules just when it's in solution. And when we add ammonia to it, we can create this ammonia complex here. So each of those water molecules is displaced by an ammonia molecule. And this is a blue-violet complex here. Okay, so this blue-violet is really this color. When addition of aqueous ammonia leads to precipitation, you're seeing the effect of ammonia as a weak base. So the precipitate is a hydroxide. And you can compare those precipitates with when you've added just hydroxide to a metal cation. You can compare and see if, okay, is this really the hydroxide? And you can compare them. However, because ammonia is such a weak base, okay, the concentration of that OH that's formed isn't large enough to redissolve the amphoteric hydroxides. So that's a good way to make a hydroxide and not redissolve it. So when the ammonia is acting as a ligand and forming a complex, you're not seeing the precipitate, but oftentimes what you're seeing is an observable color change. So that's what you want to look for. So here's an example where copper ion with ammonia can form this copper ammonia complex. And my colors here have been shifted, but this light blue is just the copper in solution associated with the water molecules. And here, the copper being associated with the ammonia is dark blue. So you see this light blue to dark blue transition, and then that's what tells you that you're forming this ammonia complex. The colors of the ammonia complexes of the transition metals are quite characteristic in their color, and these colors can be used to help identify the ion, which is the objective of this lab, is to find out and identify what ions are in your unknown solution. So let's talk about the unknown solution. All the unknowns contain 2 cations. One is colored in aqueous solution and the other is colorless. So that will give you a clue as to what one of your ions is just by observing the initial solution that you obtain. I'm not going to go through the separate types of schemes that you could come up with here because this is part of the lab. You need to come up with what type of scheme can separate your ions, okay? So once you have your data of what your known ions do when you react them with hydroxides and ammonia and all of the steps that we just went through, that information should be enough to give you the ability to work out a scheme to separate your 2 ions and identify what they are. There are notes of advice and caution in the lab manual. So I'm not going to go through each one, but just note that they're in there and they are critical really to help you come up with what type of scheme you should be using. Now, as you work on your unknown solution and your knowns, be sure to write down your observations completely. Okay, so that way your instructor can help you identify any errors that you've made, and you'll also have a nice complete set of observations to include in your report. All right, so here's your report. You need to submit a fully typed lab report. Be sure to include all your observations under your data section. Include your separation scheme for your unknown as part of your procedure. You need to describe exactly what you did, and you can't simply reference the manual for the procedure on this lab because you're writing part of the procedure. In your conclusion section, make sure that you identify which ions were in your unknown and what your unknown number was, okay? In addition, you need to support your conclusions with data. Okay, this is what I did, this is what I saw, this is why I'm concluding that it is, say, an aluminum ion, and explain with a rationale. And this concludes your pre-lab video.